All right, welcome everyone. So last time we introduced matrices and learned all kinds of characteristics of matrices and all kinds of things that we can do with it or with them. And one of the things that we've also seen is that it fits very nicely into the vector concept that we introduced at the beginning. In a way, if we interpret a vector as an n cross 1 matrix, so for example in 2D we take 2 cross 1, or in 3D a 3 cross 1 matrix, then we can consider a vector as a matrix and can do all the matrix operations also with the vectors and can mix the operations with each other. So here is an example again in 2D and in 3D where we make a matrix multiplication of a matrix and a vector, which is a very special case of a vector. And the interesting thing here that you see is that the end result, although it looks like a big matrix, but there are plus signs in between. So if you look at the values, you see these are all scalar values. So we again have an m cross n matrix as a result because of the way how the matrix multiplication was defined. And that means the end result is also a vector. So what we can do with matrix multiplication is we can use it to manipulate or to transform vectors. And this is what we're going to talk about today. We're going to talk about vector transformation. And here is just a simple example to illustrate it, a simple case to illustrate it with a concrete example, which is scaling by a factor of 2 with respect to the origin. So for example, if you think about, you have an object like a square here that is represented by 4 points or 4 vectors that represent these 4 points. Then we have this vector here, and that has this is the x-coordinate of the vector. Now, if you multiply this vector with a matrix 2, 0, 0, 2, you get as a result, obviously, for the first coordinate, 2x plus 0. So you get twice the original value. So you go here up to 2 times x, if this is x. And then you end up at this point here. Same for this value here, you end up here, and for the others as well. In the x direction and also in the y direction, you scale all the values by a factor of 2. So if you have an object like this, you apply the matrix to it with matrix multiplication, or to all the vectors that represent this object, you can just enlarge it by a factor of 2 with respect to the origin. And there are all of other kinds of matrices that we can create that allow us to transform an object or a vector in different ways. And all these transformations are called linear transformations. And the reason is that if you do a matrix multiplication with a vector, it always fulfills 2 criteria. The first criteria is if you apply this transformation to a vector that is the sum of 2 individual vectors, you can also apply the transformation to each individual vector and then add them up, and then you get the same result, which is illustrated here in the image. So if you have this vector v, for example, and the vector u, and you apply the transformation to the individual vectors and then you add them up, then you add them up, here I have to draw it, then you get the very same vector that you would get if you first add the vectors up and then apply the transformation. The second characteristic is if you multiply the vector with a scalar and then apply the transformation, you get the same result as if you apply the transformation to the vector and then multiply it with the scalar. And if those 2 characteristics are fulfilled, we say we have a linear transformation. And the interesting thing is, or the clue with this is why I'm doing this, is that linear transformations can be represented with matrix transformations, matrix multiplication, or the other way around. If something is created with a matrix multiplication, we call it a linear transformation, and it fulfills these criteria. Alternatively to these 2 criteria, you can also have just 1 criteria, which basically summarizes the 2 criteria into 1. So you have, instead of the addition of 2 vectors, you have the addition of 2 vectors multiplied with a scalar, and that is then the same as if you apply the transformation to the individual vectors first and then do all the other operations. If you, for example, a very common exercise in question in exams is to show that something is a matrix is a linear transformation, and then you have to prove either the first and the second statement, or alternatively you can just prove the third statement, which saves you a little writing time. Good. So, like I said, linear transformations can be represented by matrices or the other way around. So let's look at a couple of examples. We already saw an example, scaling by a factor of 2. But of course, we don't have to scale by a factor of 2. We can scale by any factor. And we do this in 2D by just using a matrix where we have values in the diagonal and all the other values are 0. So if we multiply this with a vector, I wrote it down here to make it really clear, but you see these things here are 0, so we only get a scalar multiplication with the coordinate, which is a scaling function. So I'm going through this now with I will do it only with 2D, because it's the generalization to 3D is in most cases just pretty straightforward, but the more complicated things are of course easier to understand in 2D, which is why we'll only talk about 2D in the first part, and then later on we will generalize it to 3D. Good. So you see here this is pretty straightforward and pretty obvious. We can do a scaling, but we do not only have to do a uniform scaling where we scale in both directions in the same way, but we can also give the scaling coefficients different values, and then we can scale in different about different sizes in each direction. And also we do not only have to enlarge it, but we can also shrink sizes. So for example, here we have a first coefficient is smaller than 1. So the x-coordinate here, the original x-coordinate, gets half. So the point here moves from here to here on the x-coordinate. In the y-coordinate, we have a different value. We're doing a scaling by 3. So the y value here moves up to here. So we see here we have a transformation of this, which is not uniform. Now, question here, what is the inverse matrix of that? And now I realized when I did this slide here that this year we have the tutorial switched on Thursday, which is why this is actually not in line with the tutorials, because that is part of the next tutorial. So I have to explain it now. How we get the inverse matrix of a matrix. You remember last time I introduced an inverse matrix is a matrix that if you multiply the matrix with the inverse matrix, you get the identity matrix. And the question is, how do we calculate the inverse matrix from a matrix? And I told you already last time that you can do this with Gaussian elimination, but I didn't explain you why, because it's part of the tutorial, which then later I realized is only after this lecture. So the idea how to do this, you remember in Gaussian elimination we had a matrix, and then we had a vector b here, and then we used this this Gaussian, the elimination functions, the 3 that we can use to transform it in a way here that we have here a dash, which is a unit matrix, and then we have here b dash, and that way we can easily see the solution for x and y, because here we just have the 1 and only zeros here. But now we want to have the inverse matrix, so we're not interested in solving a linear equation system. And we do this by just writing here the identity matrix and then do the transformations again in a way that we have on the left side the identity matrix, and then on the right side we get the inverse of A. And the reason why this is the case is actually quite simple to understand. If you write down the original equation here, you have AX equals I, and that is the same as A inverse times AX equals A inverse times I, because we have an equation, so we can multiply it with the same thing on both sides and we still have the same results. Now, the inverse was defined in a way that if we multiply it with the original matrix, it gives you the identity matrix, and the inverse times in the identity matrix was defined that if we multiply it with another matrix, we get the other matrix. So you see here what we have here is exactly what we have here at the bottom. And if we do this transformation with all these permitted changes that we have in the Gaussian elimination, it doesn't change the solution for the value x, which is not important here because we want the solution, but it's important because it means that we can do all this transformation and do not change it. So we just do the changes, have the same linear equation system at the end, but on the right side we have the inverse matrix. And if you do this to this matrix, it's a very simple case. Then you see obviously that this will lead to this matrix here, 2, 0, 0, 1/3. So from an arithmetic point of view, this is actually so simple you wouldn't even do Gaussian elimination, you would just write it down, because you can, if you read a little practice, you immediately see it. But from a geometric point of view, it's of course interesting to think about what this means and what this represents. And that is of course the reason why I was asking this question in the first place. What is the inverse of that matrix? Because if you look at the image, what this means, you see that the inverse is just the opposite transformation that we have here. So the x value gets doubled from 1/2. In the first case it was 1/2, so it was half of it. Now we double it, and the y value gets reduced by a factor of 1 divided by 3. So from the 3 times the original we go back now to 1/3, which means we end up at the very original. So the inverse matrix is important because we can just do a reverse transformation with it. Good. Now last time I said that the inverse matrix does not always exist. And I also said that later on, when we look at how we can use it, a geometric interpretation of it, we will also understand why it cannot always exist. And the example comes now, which is a transformation that is called the orthographic projection. If we have an object and we project it towards one of the coordinates, for example, in this case, we project it towards the y coordinate, the y-axis, which means for the transformation matrix, we just set all values 0 but the y value, which means all values are 0 except for the y, which is obviously a projection towards the y axis. But then we cannot create an inverse transformation of it, because if you think about it geometrically, you don't know. If you just have the projection and say, I want to make a reverse transformation now, there are different possibilities. So this, for example, would be the very same transformation if you do an orthographic projection. So there are multiple solutions for the inverse, which means a unique inverse is not defined. Likewise, if you do it arithmetically with Gaussian elimination, you will realize that you cannot do it, because here you have this whole line with 0, and that was this one case that we had last time when we were talked about solving linear equation system. We had 0x plus 0y plus 0z equals something unequal to 0, and then there was no solution for it. Or if it equals 0, there are an infinite number of solutions of it. That is actually this case here, because we have 0 here on the right side. So there is an infinite number of solutions, but that makes also sense geometrically, because we see here that there is an infinite number of options how we can create this in the first place. So of course the other way around has an infinite number of solutions. Good. Another example, also rather simple, if you look at the image, is reflection at the line y equals x. So this here is the line y equals x. And if you think about what happens to an object if you mirror it on that line, then you will see that it basically just swaps the x and the y coordinate. So if you here have a point x, y, so this is x and this is y, then you see if you mirror it, this here becomes the y becomes the x, and the x becomes the y. So you just swap it. So if you write this down here, you see you have 0 plus 0x plus y. So you have the y value here, and here in the second line you have x plus 0y, which means you have the x value here. So you just swapped it. And the inverse matrix with Gaussian elimination, this is very simple, because this is actually the one rule that we didn't use last time, which is we can just exchange two lines. So if you apply Gaussian here, you just change these two lines here, and then you get the inverse matrix, which in that case is exactly the same. So A inverse is the same as A, which also makes sense geometrically, because the reverse operation over reflection is just reflected back. So it's just the same operation. We just flip the coordinates again, and then we end up at the same object. Good. Another operation is so-called shearing. Shearing, I already used this phrase in relation to parallelograms last time when I did this proof where I said if you shear a parallelogram, the volume doesn't change. So shearing in a certain direction, for example in x direction, basically means we're pushing everything in that direction, and the pushing depends on the y, the value of the y value of the coordinate or of the vector. So for example here, if we here have y, sorry, here we have x, then the y position doesn't change, but the new x position is x plus y, which actually in that case is not the green one. So here x would be 1, and it is, yeah, and y is 4, so that would be 5. Yeah, it is. So that would be this here. So this here is now x plus y. And you see here, obviously, because it depends on y, the more we're up, the more we're pushing it to the right side, and the lower we're down, the less we're pushing it, but we're always pushing it to the right side. Unless we're negative, of course, then we subtract it. Likewise, we can also, of course, push things upwards or downwards. So, for example, for the second matrix at the bottom here, if we have something like this, then we can also push it downwards. But again, we do not move the whole thing, but we're just pushing one side depending on how far away we are from the axis. Of course, we cannot only push this with a constant value, but we can also have a general case where we multiply this with a scalar here, and then we can push things even further. So for example, we can take this here and can push it really up to here or even further by just having a larger s value. And the inverse of it, okay, of course we can calculate the inverse matrix with Gaussian, but we can also look at the image, and then we immediately see that the inverse operation of a shearing is of course again a shearing, but we're just pushing it in a different side. So we just change the sign of the scalar value that we multiply with, and then we just basically push everything back, and then we're back at the original image. Good. Now another linear transformation is the rotation around the origin. It looks a little more complicated, but that's because here the example with 45 degree is, if you calculate it, that's the square root of 2 divided by 2. This is actually the general case that you should remember. This is a rotation around an angle of 45 degree around the origin. So this is the trigonomic relationship that we have between these angles. So the idea is we have a point here, we want to move it here with a specific angle. In that case, this is 45 degree. And then we have to multiply it with this matrix, and then we end up at this point. And we will see later why this actually is a transformation in that, why this actually is a rotation. And the general case, of course, is then not 45 degrees, but just take an angle phi, and then we can rotate around any kind of angle that we set there. And this is a counterclockwise rotation. If we do it a clockwise rotation, we use this matrix here at the bottom, and the relation between the two is easy to see if you remember the sine and the cosine function, because the cosine function is axis symmetric, whereas the sine function is point symmetric. So if you look at the cosine of minus phi, that is the same as the cosine of phi, and the sine of minus phi, because it's point symmetric, is minus the sine of phi. Now if we want to rotate this not by phi clockwise but counterclockwise, that means we're just rotating it by the angle minus phi. So we're just taking the angle minus phi in here, and then we get, of course, here end up with this rotation matrix. So that relation is quite easy to see, but of course the question remains, how did I come up with cosine and sine, and why is this really a rotation? Or the general question, of course, these rotation, all these matrices, the scaling, and so they are very intuitive and very simple. So by sitting down, drawing, you easily can come up with the solution. But of course, there are more complicated situations. So we want to figure out what is a good way to figure out how we can create these matrices, how a transformation matrix for a specific case looks like, and to understand how we can do this. It's just a good opportunity also to repeat what we have done, because there were already quite a lot. We have already learned about 4 different matrices. So let's see what happens if I apply these matrices to the base vectors of a Cartesian coordinate system, which is 1, 0 and 0, 1. For the scaling, we say that's a matrix where we have 2 coefficients. So the result will be just a multiple of the first coordinate 0, and in the second case 0, and then the scaling factor b for the y coordinate. For the shearing, it will be, in the first case nothing happens, it stays 1, 0, and in the second, because that's the x-axis, so if you remember the image, there's nothing happening in that direction. But if you look at, then remember the other direction, then you have s1. So the x value shifts in that direction, but the y value stays at the same level. For the reflection, we said we just swap the lines, which happens if you multiply it with that matrix. Swap the lines, we swap the coordinates. 0, 1, 1, 0. And if we do the rotation, we get square root of 2 divided by 2, 1, 1. And we get square root of 2 divided by 2 minus 1, 1. I already said this last year. If anyone knows a better presentation system that you can also annotate than Adobe Acrobat, please let me know, because it's horrible, but I don't know a better one. Anyway, so you see here, this is what happens when we apply these matrices that we already learned. Now, if you look at the result and if you look at the matrix and then ask yourself the question again, how do we come up with those matrices? I hope you see the relation, because these are exactly the same values that we have here. So the column value vectors of these transformations that we have are the images of the base vectors if we apply the transformation to it. And this is not a coincidence. So let's see why this is actually a general case. Because remember what I said last time? I said last time you cannot prove a general case by just showing a few examples. And that's what I just did. I showed you a few examples and I said, yeah, this is always the case. So we have to look into, or at least try to understand why this is indeed the case. And this is indeed a case because it is a matrix transformation is a linear transformation. So we have to remember this definition again of a linear transformation. So you remember there were these 2 conditions, or the third condition, and I said if you use the third one you save some writing, which is why I'm doing this now. So if we have a vector in Cartesian coordinates with this base vectors b1 and b0, we can write it as a linear combination of these 2 vectors. So the vector xy can be written like this, that we have the factor x multiplied by the first base vector and the vector y multiplied by the second base vector. Now if we apply a linear transformation to it, because it is a linear transformation, it must fulfill this condition here. That means we can also write it that way here. So we get the transformation applied to each individual base vector and then multiplied with the scalar value and then summed up. Now if you look at, for example, this part here, this is a matrix multiplication with a vector 1, 0, or if we go to higher dimension, a vector 1, 0, 0. And if you multiply that with a matrix, if you remember how matrix multiplication is defined, you will see that we always end up with a vector that is exactly the first column of the matrix. Same for the second base vector, we end up with the second column, and if we have multiple dimensions, the same for the east column. If east base index, we end up with the east columns of the matrix. But that also means, of course, the other way around. If we want to find the matrix, we just have to figure out what is the image of the base vector when we do the transformation to it, and then we can write down the matrix. And we'll see this now with this transformation matrix. So we'll see now why this is indeed a transformation, a rotation around the origin. And we can see that by, let's look at it by the first base vector. The second then is, you can do it at home as an exercise, but it's pretty straightforward, same case. You have a base vector 1, 0, and we want to rotate it clockwise, counterclockwise around the angle phi. So we end up with a vector here. So that vector here has the coordinates, the new coordinates x1 and y1. And these are the new coordinates that make our first column vector, because that is the image after we apply the transformation to this base vector. And if you look at this in a triangle, and now you remember Cartesian coordinate system, we have unit vectors, so the length here is 1. And if you now remember the trigonometric relationships in a triangle, you have the cosine of phi is x1 divided by 1, and the sine of phi is y1 divided by 1, and then you see exactly that these are the values that you get for this image. So this is our first vector, our first column here, and for the second you can prove it in a similar way. Good, so we know now how we can create these matrices for simple transformations, but of course when we use this then in graphics we can also do a transformation, then we get an object, and we can apply another transformation. So we just take the vector that results from this first matrix multiplication and multiply it with another vector, and that way we can, for example, like here, we can start by doing a reflection, and then we scale the result, and then we get from the yellow over the gray one to this green box here that is illustrated. But we also know from last time from matrix multiplication that matrix multiplication is associative. So arithmetically, we could also just combine. It doesn't matter if we first multiply the vector, which is a special matrix, with the first matrix and then with the other matrix, or if we first multiply the first two matrices and then the last one, and then the vector. So we can combine these two transformations into one, and then have just one matrix multiplication to do both transformations. What we cannot do, of course, is we cannot change the order, because I hope you also remember that matrix multiplication is not commutative. So it is a difference if we apply first the scaling and then the rotation, or the other way around, which you can also see here arithmetically where I did the calculations, and you see that you end up having a different vector, a different result in the end. And also if you draw the second image for the second line, so this is the image for the first transformation, if you draw the image for the transformation in the second line, if you first do the scaling and then do the reflection, obviously you end up with a different object than you would do in this case. Good. So it is always important when we do a transformation that we do it from a vector that we applied from this side here, that we apply the first transformation first and then the second one here. This is also a common mistake in exams when you create a transformation matrix that does first this operation and then that operation, that people mess up the order. Good. So we have to be careful with the order. Another thing we have to be careful about is normal vectors. So you can imagine, this transformation can be easily used in graphics if you have an object and then you want to transform the object to display it in a slightly different, in a transformed way or at a different place. Then you just multiply all the coordinates or the vectors representing that object with the matrix. And if you have already done light calculation, you already have the normal vectors, then you can also just multiply the normal vectors with this matrix, and you have to transform normal vectors. But that unfortunately doesn't work, because you see it easily here with an example that if you do the shearing, you see that the tangent vector is actually transformed correctly, but the normal vector is not, because the normal vector doesn't change when you apply the shearing, which this in this direction, because the x values, the y value stays the same, so the normal vector doesn't fit anymore. So you have to do something different. Fortunately, you can do this by just applying a different matrix to it. So let's see why this is actually the matrix that always leads to a correct normal vector transformation. It's the inverse matrix, the transposed of the inverse matrix of the transformation matrix. Let's look at this because it's actually quite simple. We said we know that the tangent vectors are transformed correctly. So if we have a tangent vector and apply the transformation matrix to it, we get another vector, of course, but that vector is then still a correct tangent vector to our object at that position. But we say that we see in the example, in the image, that if we apply the transformation vector to a normal vector, it is not necessarily the same, the correct normal vector. So what we want here, our goal is, we want to find a correct transformation matrix, and I'm claiming that this is the correct transformation matrix that gives us the correct normal vector. And we see that by looking, first we can say the normal vector, the transpose of the normal vector multiplied with a tangent vector is 0, because we know, you remember, a normal vector to a surface is defined as a vector perpendicular to the surface tangent vector. So the scalar product of them must be 0. But then we can also write it this way. We just put in here the identity matrix, because we know multiplying with the identity matrix doesn't change the result. And we also know that a matrix multiplied with her inverse is the same, leads to the identity matrix, so we can also write it in that way. But we see also here that this here on the right side is exactly our perfect tangent vector, so we can write it that way. We have here the tangent vector. Here we have the left side of this equation. And now we know that the scalar product is 0, which means that this vector that we get by the multiplication here must be perpendicular to this tangent vector. But if it is perpendicular to the tangent vector, it is a normal vector to it, to the object, so this is exactly the vector that we are looking for. The only thing is we have here a transpose now, and we want to have the real vector, so we just have to make a transposed again, because the transposed of the transposed is the original one, and then we get here the original vector, but here we have then the transposed. Now if you remember again, last time I made a proof of this characteristic here, and that shows that this here, if we bring the transposed inside, we have to just switch the order, and that means we have exactly what we wanted, namely we have found a matrix NA. If we multiply the normal vector to it, we get the correct normal vector to this after the transformation. And that is exactly the same matrix that I claimed here is the one you have to use. Good. So, yeah, so we know now that we can do transformation with matrices and that we can compose them to do more complex transformations. So let's look at more complicated examples. For example, we said we already had a rotation around the origin. Now let's look at a rotation around a random point. So for example, around the point 2, 1. How could we do that? Well, we can, of course, split it in simple steps, simpler transformations. We can, for example, say we move everything to the origin, because we already know how to make a rotation around the origin. Then we rotate around the origin, and then we move everything back, and then we have rotated around that point from which we were moving everything. And we already know everything we need to do here. We know how to rotate, we know how to combine compose the transformations into one. The only thing we don't know is how to translate. Problem is, we cannot do this with matrix multiplication, because translation is not a linear operation. And you can see this by just writing down what you get with a linear transformation. If you multiply a matrix with a vector, you will always end up having something like this here. And what we want for linear transformation, for a translation, is we just want to add a constant value to our coordinates x and y. So we just want to have everything, for example, if everything is above the 2 above the origin, we just want to have the y value minus 2, but we cannot achieve this. So if you want to have, for example, here y minus 2, there is no way that you can set the coordinates here in a way that you achieve that. I actually recommend that you sit down at home and really try to do this. Some people see this obviously at a first sight, but some people, last year I realized that some people really had problems seeing this. Why are we doing, why is this a problem in the first place? And then it helps you much better understanding it if you really understand why we're doing this and that this really doesn't work. The point is, of course, because you're always multiplying here with something, with a non-constant value. So, and what we would need is a constant value here, and there is no way to get this y, this x or this y here away other than setting it 0, which, of course, then you don't have a translation. Good. The other thing that I realized last year that people didn't understand why this is a problem. They ask, why can I not just add a vector to it when I want to do a translation? Why do you want to do a matrix multiplication? The point is that with this matrix multiplication, we have a very simple and straightforward framework to do the multiplication, and it would be, of course, very convenient if we could do this one other transformation also with the matrix framework. First of all, of course, all the graphics hardware supports matrix multiplication, but they don't support vector addition. So if we want to implement it with the graphics hardware, we have to stick to what the hardware supports. Of course, the other reason why the hardware supports it is because it is so convenient to do it with matrices. So even if you implement it in software, if you do a transformation and do it with matrix multiplication, and there is one transformation that you have to do a different way, it's of course more difficult to implement. It makes the code much less structured and less clean than if you can do all kind of transformations with the very same mechanism. And that's why it would be very convenient if we could do this translation also with matrix multiplication. And the good answer, and that's also why all the hardware supports only matrix multiplication, is that it is actually doable. And for that we need these so-called homogeneous coordinates, which I want to motivate now with an example, because I also realize that this is sometimes hard to understand for people. So the idea is it is related to this shearing of objects that we had earlier. If you look at the shearing in 2D, what we said is if we are, for example, here at one level on the y-axis, what we do is we multiply all the values here with a certain value and then move it over there. And the same for this value, we move it over here. So we move everything along this line, which is this, what I said, pushing sideways, but it doesn't move up or down, it only moves sideways. And now this is the one time where I have to go ahead and look for the 3D case, because the 3D case, like I said, is a straightforward generalization of the 2D case. Instead of 2D here, instead of a rectangle, we now have a box here. And if we push that to one side, but stay within that same level, of course we get the very same thing. We move this over here. So instead of here moving this part here along the line, we move this rectangle here within the plane at this position, which is, for example, z equals d. And now if you listen carefully to what I said we'll move the box or the rectangle along the plane or the line. And that's exactly what we want. We want to move objects by matrix multiplication, and we move it by doing shearing. Shearing is a matrix multiplication. So we can move, in this case, objects in 2D by doing a matrix multiplication in 3D. We cannot do it by doing a matrix multiplication in 2D, but we can do it in 3D if we look only at that plane. And if you remember if you think about what is a plane in a 3D space, a plane can be seen as a 2D subspace of a 3D space. If you remember how when I introduced the parametric representation, I compared the two direction vectors of a plane to the two base vectors of a 2D space. So the plane is a 2D subspace. So if we want to move in this 2D subspace, in a 2D space, we can consider it as a 2D subspace of a 3D space, and then we can do the shearing. And this is let's just go through the basic idea of it. So we have a 2D space, and we have, for example, here a point xy, and then we go to a 3D space because we said we can do only the shearing only in 3D, or the shearing to make up for do the movements by doing a shearing. So we just add a certain value here, let's call it d, and that means the original point is xy0 because we're in 3D now, and the new point is xyd. Then we apply the shearing here, which means this point doesn't change, but this point here becomes now x plus some value delta, y plus delta, and a value d. That doesn't change because we stay within that plane. And now we've seen we have moved that within that plane, but originally we were in this space here. So what we can do here is we can just do an orthogonal projection of this here. So here we have x plus delta, y plus delta, d. And if we then do an orthogonal projection, we just have x plus delta, y plus delta 0. And that is exactly our original point moved by this delta here, which is a translation, but we did it by multiplying it with a matrix in 3D. So this is basically the idea of homogeneous coordinates. We take a shearing matrix in 3D, multiply it with a 2D vector that gets extended or moved into this dimension by a factor of d in this plane at this level. Then we do the multiplication to get this. Now, and this is of course what we want for the first two coordinates. But of course we have a coordinate here that doesn't fit. And also we don't know what the matrix actually looks like. So let's look at shearing in 3D in direction of the xy direction. So in a plane, in a plane parallel to the xy plane. And if we do that, you see you end up here with something that looks almost like what we want, but we have here still this factor of d, and we have this value here, which is also not what we want. But if you think about, we didn't make any assumptions about d. As I just said, we just have to go a level up to some level. It doesn't really matter which one, because we're only interested in the orthogonal projection then later. And if we go higher up, the shearing moves it just a little. No, then the forget what I said. We didn't make an assumption about d, so we can also set the d to 1. And if we set the d to 1, then you see we'll end up exactly what we want. We have here x plus t, x plus xt, y plus yt, and 1. And this is the result that we want. And this is the matrix that we need for that. And we see now that this works if we present a point with a vector like this. Then we can translate the first two coordinates, and the last coordinate stays at 1. So the homogeneous coordinates say we have to add a 1 to each point, and then we can translate it. Now a question now is translating. If you remember at the very beginning, I said a vector is defined by its length and its direction. But that means we cannot translate a vector, because if we move a vector to a different position, it still has the same length and the same direction. So if we use that with a vector, or if we use that x, y, and then a 1 and apply it to a vector, we get a different result, but we cannot translate a vector. We can only vectors that represent a point. We can translate the point, but we cannot translate the vector itself. So we have to represent vectors differently, and we do this by writing a 0 here. So if we multiply that with the matrix, you see you do not transform the matrix, of course, because how it is designed. You see that this 0 removes these things here, so the vector stays the same. So this is a way how we can represent a vector, and the whole framework fits and works out very well. So and this altogether is called homogeneous coordinates, and the whole system, when we apply this, and with this we can then also do translations. And if we wait, sorry, I just remembered I have to say that, because that's also a common mistake, and I forgot to say it at the beginning. We have the linear transformations can be done by matrix multiplication, or if we can do it with a matrix multiplication, we call it a linear transformation. But then I said that we cannot do translations with matrix multiplication, which means, and that is then called the affine transformation, and that's a common mistake that people misunderstood last year. An affine transformation is a transformation that combines linear transformation and translation, and not just translation. A lot of people last year misinterpreted it and thought affine transformation is only a translation. That's not the case. We have linear transformation and translation, and when we have both, then we have an affine transformation. And to do that affine transformation, we need homogeneous coordinates. So we need to represent points or locations by a vector where we add another coordinate, a third coordinate, which is 1. We need to represent vectors with a third coordinate that is 0. And we need to represent matrices with a lower row that has only zeros and ones, because with that, if we do then a matrix multiplication, we can guarantee that we can use this column here to add factors here that are then the constant values that are added to the first coordinates, and that allow us then to do the translation. And we see a couple of examples of this then later after the break.